So this is part 4 of lesson 1, and this time we are comparing the graphs of the function f of x equals 2 to the power of x. It's a basic exponential function, and f of x equals 2 to the power of 3x. And what we notice here is that we have changed the coefficient from k equals 1 to k equals 3. Just to refresh your memory or to recall again, the changes in the k coefficient will affect the horizontal stretches of the graph of a function, and we remember that when k is the absolute value of k is bigger than 1, and I'm going to make a note in here. So when the absolute value of k is bigger than 1, the function undergoes horizontal compression, so it is narrower. So we're going to check and see what the graphs would look like. We're going to use Desmos for this. So I already typed in 2 to the x and 2 to the 3x. 2 to the x is the purple graph, and 2 to the power 3x is the orange graph. So you can tell that the orange graph is closer to the y-axis. The y-intercept hasn't changed, and I'm going to sketch both of them here on our graphs. So on our grid, I meant. So here is x equals 0, y equals 1. And we had the purple graph for 2 to the power of x. And we had the orange graph for 2 to the power of 3x. Okay, so let's get graphing. And say this was the graph. Okay. And 2 to the power 3x had the same y-intercept, but it appeared to be closer to the y-axis. Okay, so and I'm going to quickly write domain, range, and y-intercept. They're the same. Actually, for any exponential function, domain is any real number x, y is positive, and y-intercept is 1. Now I want to talk about something very important. So in here, now we know that the changes in the value of k will change the horizontal stretches of a graph. Here k is bigger than 1, so with a k of 3 we expect the graph to be narrower. So what that means is that we're going to expect the graph to reach the same height for values of y that for values of x that are 3 times as small. That's because of the coefficient k. So if, for example, we had this width of the graph for the function y equals 2 to the power of x, for the function y equals 2 to the power 3x, the width would be 1/3 of what it is for the purple graph. Okay, and that is thanks to the coefficient k, which is 3. That empowers the values of x. So for x is 3 times as small, the orange graph will reach the same y values as the x, as in the 2 to the power of x. Now, and probably some of you are thinking about this already. So when we look at the horizontal compression in an exponential function, you can also interpret this as a vertical expansion, right? Because the graph does appear to be narrower, and sometimes when it is narrower, we expect it to be taller as well. Now, why is that? If you take a look at a 2 to the power of 3x, this can also be 2 to the power of 3 to the power of x, and that would be 8 to the power of x. Okay, so the base 8 in here apparently is bigger than the base 2 in 2 to the power of x, right? And we're talking about 2 to the 2 different functions in here. So there is an overlap in the transformations of the graphs of exponential functions. So what does that mean, or what do I mean by that? So sometimes horizontal compression or expansion can be interpreted as a vertical expansion or as a change in the base of a function. So there are multiple interpretations or equations of a same graph, and one graph can have or can be described by more than one equation. So in this case, we're going to say that 2 to the power of 3x, so the purple graph here, can be seen as, well, what it is, y equals 2 to the power of 3x, but it can also be seen as y equals 8 to the power of x. So just so that we keep that in mind. And now we're going to move on to the changes of k. K is 0.5 this time. So again, graph using Desmos. And I'm just going to simply change the coefficient in here, make it 0.5. It's kind of funny what it happened when k was 0 again, right? So you see we have a straight line, and that's what's good about using technology. But in the meantime, we have to keep our senses sharp and try to notice these changes and transformations. Anyhow, so here we go again. We are going to graph both functions, and I think that this would be our purple graph here. Okay, so y equals 2 to the power of x, and y equals 2 to the power of 0.5x. So we're going to see that the same y values here are achieved for x values twice as big as in the purple graph. And this y value will be reached in here. So here we go. That wasn't very good drawing. Let me just fix this very quickly. Okay, and it's going to be down here. Good enough, I guess. So we're going to say that the domain for this function, again, x any real number, y bigger than 0, y-intercept equals 1. Okay, so again, very quickly, we're going to mention the fact that here are the values of k. So for k values between -1 and +1, we're going to see that the graph will undergo horizontal expansion. Bigger than 1 and less than -1, it's going to be a horizontal compression. All right, and keep in mind that k cannot equal 0. So if 0 is in here, we're going to have an empty circle. All right, the next change that we are going to observe is the changes in the values of h, where h actually represents the horizontal translation. So we're going to graph both functions, 2 to the x and 2 to the x minus 3. Okay. Y equals 2 to the power of x minus 3. Okay, so I wish it shows a different color. Do I have the... Okay, so let's take a look at these two graphs, because it seems that we have some substantial changes in here in the features of the graph. So this is y equals 2 to the power of x with y-intercept at 0, 1. And this one here is y equals 2 to the power of x minus 3. And we see that the y-intercept has changed to become 0.125. So that's 1/8. So why did this happen, right? So what changed the y-intercept? Apparently, the coefficient h, or translating it 3 units to the right. So whatever the y value used to be at, sorry, let's take a look at 2 to the x. So 2 to the x, we had the y value of 0.125. Let's walk along it. 0.125. Okay, my pen is not letting me see. Okay, 0.125 at -3, right? So you see that at -3, y equals 2 to the power of x had the value of 0.125. Now, this y value of 0.125 for the 2 to the power x minus 3 has happened at x equals 0, so 3 units after. Okay, so let's go back to our graphs now and sketch them. So we had one graph, what was purple, the other one was kind of pink, but it doesn't really matter. Just gonna make it blue for now. And starting with 2 to the power of x, that's what we had in here, and 2 to the power of x minus 3, so this value here was achieved right here. So the shape of the graph won't change, okay? So shape remains the same, unlike in the cases when k and a changed. The domain is still x any real number, the range is y bigger than 0, but the y-intercept is changing, right? So the y-intercept was 1 for 2 to the power of x and 0.125 for 2 to the x minus 3. Now, in a similar way, we are going to go ahead and graph y equals 1/2 to the power of x and 1/2 to the power of x plus 2. So I just changed the basis a little bit, just for the fun of it. We're kind of getting tired of 2 to the power of x. And I'm gonna move on to y equals 1/2 or 0.5 to the power of x. And the next one was 0.5 to the power of x plus 2, I think. Let's double check, yes. Y equals 0.5 to the power of x plus 2. Okay, and up here. Why is this happening? I think that needs brackets. It does it all the time. All right. So here go both graphs. So y equals 0.5 to the power of x is the gray graph right here, and 0.5x plus 2 is the blue graph. Now, you can notice here how the y-intercept is 1 for 0.5 to the power of x, and 0.5 to the power of x plus 2, let's double check, is 0.25. So I'm going to check and see where on the basic graph 0.5 to the power of x on the white graph was the y value 0.125, and okay, so I'm gonna double check in here. So it was 0. Here. So 0.25 for this one was at this point here, right? At x equals 2, sorry, it keeps moving. At x equals 2, y was 0.25, so it was 2 units later, right? So we are going to say that if we have 1/2 to the power of x here, let me just set the colors. So I'm going to make this one blue, and I'll make this one here orange, and I'm going to say that here's the y-intercept of 1, here goes 1/2 to the power of x, and the other graph, so the y-intercept will be 0.25 here, okay, right here. So the shape of the graph will stay the same, sorry, but we are going to see a translation, and that's what moves the y-intercept. So we're going to say that x is any real number, and y is bigger than 0, and the y-intercept here changed to become 0.25, so 1/4. Now, again, the shape remains the same, but the y-intercept will change. That's thanks to the shift, the horizontal shift. So changing the value of d is going to change the vertical translation of the graph. We're graphing 3 to the x and 3 to the x plus 2. So y equals 3 to the x. And y equals 3 to the power of x then plus 2. Okay, so y equals 3 to the power of x is the orange graph, and 3 to the power of x plus 2 is the pink graph. You can see quite a few noticeable things. So the y-intercept is 0, 1 for 3 to the x, and the y-intercept is at 0, 3 for the 3 to the power of x plus 2. So it seems that the graph has moved vertically up, and so has the y-intercept. So the y-intercept has moved by 2 units from 1 to 3. Now, just like the y-intercept moves, so that's the horizontal asymptote. Remember, asymptotes move with their graphs. And we're going to sketch them again. So I'm going to pick 2 colors. We're going orange and purple. They go together, actually. So here we go. So y equals 3 to the power of x. And y equals 3 to the power of x plus 2. So if this is 1, 2, 3, so the y-intercept will be at 3 here. The shape of the graph is not supposed to change, right? The asymptote was at 0, and now it's gonna move at 2. Oopsie, that was okay. So the asymptote will be right here. Oh, okay. So I always have a hard time with this for some reason. Okay, bigger we can be. So that's the horizontal asymptote for the orange graph, and this one here would be the horizontal asymptote for the purple graph. The next one is 1 over 2 to the power of x and 1 over 2 power x minus 4. I'm not going to use decimals in here. I think I know what's going to happen, and I'm going to draw the graphs right away. I am going to make this one purple and this one here orange, and y equals 1/2 to the power of x. We'll have the y-intercept right here at 1, and the graph will go down this way. And take away 4 means that the y-intercept will go from 1 to negative, probably -1, -2, -3. You know what? I'm just going to quickly change the scale in here, all right? Because I haven't done a good job with setting the axis. And actually, I'm going to try something. Good. I think this works. We've got to be creative sometimes. So I'm going to draw the horizontal axis a little bit higher than what I have. So I'm going to draw the horizontal axis somewhere in here. Okay. So this would be my x-axis, my new x-axis, and this is the y-axis. Great, it worked out. And I'm going to start by graphing my purple graph. 1 over 2 to the power of x, y-intercept is 1, and the graph will go this way down. And y equals 1 over 2 power of x minus 4. We'll move the y-intercept from 1 to 1, 2, 3, 4 units down. Okay, and 4 units down will bring the y-intercept at -3. The shape of the graph is not supposed to change. And talking about the asymptotes, we are going to say that the asymptote for 1/2 to the power of x will be here, and the asymptote for 1 over 2 power x minus 4 will be at negative 4. So the asymptote will be somewhere in here. Not always looking graphs, but the idea is there. And we have x an real number, y is bigger than 0, and the y-intercept has changed from y equals 1 to y equals negative 3, so 4 units down, thanks to the vertical translation. So this is the lesson actually, and the rest of it is practice. So I invite you to quickly sketch all these graphs. We have multiple transformations in some of them, and have fun. It's only 4